Assalamu alaikum wa rahmatullahi wa barakatuh. Don't forget today we have quiz. Okay. So share screen. Okay. Yeah, in our previous class yesterday, we have started discussing about dimensions, okay? About flow dimensions. Okay. And all right, back. So we mentioned that a flow can be said to be one-dimensional, two-dimensional, or three-dimensional. If the flow velocities vary in uh, one, two, or three primary dimensions, respectively. Okay? Typically, fluid flow involves a three-dimensional geometry because the pipe, the channel, and what have you, it is a three-dimensional figure. Okay? Hence, the geometry is usually three-dimensional, which can vary in X, Y, Z, in rectangular coordinates or cylindrical coordinates using the radius, angle, and Z. Okay. However, the variation of velocity in certain directions can be small relative to the variation in other directions and can be ignored, negligible error. Okay? In such cases, the flow can be modeled conveniently as being one-dimensional, two-dimensional, okay, as the case may be, which is usually easier to analyze because the more the dimensions, the more the complexity of the flow problems, okay? Now, consider a steady flow uh, in a fluid entering from a large tank into a circular pipe, which we have shown the figure below, where we described what is meant by developing flow and fully developed flow velocity flow profile. The fluid velocity everywhere on the pipe surface is zero because of the no slip condition, isn't it? And the flow is two-dimensional and in the entrance region of the pipe, since the velocity changes in both r and z directions, but not in the theta direction. R is the radius, okay, that's the vertical direction, and z is the direction of flow in the direction of flow, okay, which is the direction of flow, which is the z direction. So this is where the figure we are, if you have water entering from a large tank, so basically the fluid is everywhere zero, okay, and it's two-dimensional at the entrance because it changes in R and Z. R, that is when you take a section, okay, and Z when you progress from one point to the other along the flow direction. The velocity changes as you can see vividly from the velocity profile, okay? Although we, took the velocity or the flow at the entrance to be uniform. That is, it has the same velocity throughout, okay, which is more or less an approximation. Okay, so the velocity profile develops fully and remains unchanged after some distance from the inlet, and the flow in this region is fully developed. Okay, so this velocity profile is maintained in the subsequent space. Okay, in the subsequent flow direction. Okay, and here the flow doesn't really vary along the theta direction. Okay, that is if we are using the cylindrical coordinate system. The fully developed flow in a circular pipe is one-dimensional. Okay, the fully developed flow is one-dimensional since the velocity varies in the radial direction only, but not in the angular or axial direction. As the flow becomes fully developed, so this velocity profile is maintained throughout. You see, it varies along R. Okay, this is R. Okay, here is maximum when R is 0, then it decreases up to when it becomes 0 at the pipe wall. Okay, the same thing down, negative R. Okay, so the flow velocity is always varying with R, but not with Z. With Z, as you move, if you select a given section, the profile is maintained throughout. Okay, the velocity profile, like if you look at this velocity here, this point, if you move a distance s, okay, it's the same velocity. Okay, so it doesn't vary along the z direction, but it varies along the r direction. So the flow reduces to a case of one-dimensional flow. Okay, reduces to a case of one-dimensional flow. All right, and the velocity profile is the same at any axial z location, and it is symmetric about the axis of the pipe. Okay, it's symmetric about the axis of the pipe. That is where you have the maximum velocity to be occurring. Note that the dimensionality of the flow also depends on the choice of coordinate system and its orientation. Okay, like for instance, in this case, the flow is one-dimensional in cylindrical coordinates. Okay, that is r, theta, and z, but two-dimensional in Cartesian coordinate system. Okay, using in Cartesian coordinates, it is two-dimensional, and this illustrates the importance of choosing the most appropriate coordinate system, for your flow problem. Okay, because the flow, when you look at the pipe section, okay, this is two-dimensional. Okay, you have y and x. So in Cartesian coordinate system, it varies along x and y, but in the cylindrical coordinate, because in cylindrical coordinate, this is also r and this is also r. So it becomes just r, which is just one dimension. Okay, so it's one dimensional in cylindrical coordinate and two dimensional in Cartesian coordinate system. Okay. So here the development of the flow, you can see at the beginning, V is equal to VRZ. It depends on the radius and Z. Then when it becomes fully developed, V becomes a function of Z alone, of R alone. Okay? So V disappears because the velocity doesn't depend on Z anymore. Okay? In the case of open channel flow, okay, all these definitions we're doing with we're considering with velocity, we will look at the depth of flow. Okay? And this, like I said, we will look at it in water engineering, CE 335. Now, still on the flow classification for the one-dimensional, if you look at a pipe flowing, okay, the velocity is a function of the radius, okay, only for one-dimensional flow, where you have the cylindrical coordinate, R and Z, okay? And then for two-dimensional flow, when you have the cross-sectional area to be like rectangular or square in shape, so it varies along x and y. Okay, x and y. Then for three-dimensional flow, if you have it tapered, okay, it is increasing in the flow direction. Okay, the cross-sectional area is increasing in the flow direction. So in this case, you have the velocity to be a function of x, y, and z. Like I told you, the more the dimensionality, I mean, it becomes the more complex the problem becomes. Okay, one-dimensional problem, two-dimensional, probably you can just use analytical method, but three-dimensional, you may have to use numerical methods, computer methods. Okay, computational methods to solve flow problems in three dimension. Okay, that's why, for the sake of, let's say, demonstration and some other stuff, we simplify it to the simplest form, one-dimensional, two-dimensional, and then for actual flow problems, we allow it to vary in three dimensions, which is the actual case. Okay. In that case, we will have to make use of the computational techniques to solve the flow problems. Now, the next topic is about boundary layer, wake, and flow separation regions. Okay. Yes. Now, flow separation occurs when the fluid particles adjacent to a body deviate from the contours of the body. This is a figure which shows flow separation behind a rod. Okay, this is like a ball, like a sphere. On flow, the streamlines deviate. Okay, this is the streamline that will hit the sphere and then will stop. The velocity of this is going to be 0. Okay, and others will move around it. Okay, so now this is a case when you have a square rod. Okay, and this is what happens. You should notice that the flow separates from the shoulders of the rod and that the wake region is large. This is the wake region. These are streamlines, okay, but this is the wake region in which the region of separated flow behind a body, okay, and this is where the flow separation occurs, okay, where the flow moves away from the wall. First, it like tries to follow it because this region is 0 and this is the boundary layer. This is the boundary layer, the thicker blue region, which is a thin region of viscous flow near a wall. Okay, the particles in contact with the sphere are going to have 0 velocity, but those farther away will have slower velocity because of the viscosity taking place, because of the shear stress, okay, because of the shear stress, okay, exerted from by the contact between the sphere and the fluid particles. Okay, so this is the boundary layer region, which we define, okay, to indicate before when defining viscous flow and inviscid flow. Okay, we also indicated the boundary layer, which is a small layer from the solid surface into some few distance above it. Okay, which is a region of viscous flow. Okay, but you can see farther away, like the farthest streamline is almost unaffected by the presence of this one. Okay, although it becomes slightly deviated. Okay, so these are regions that in which you have almost inviscid flow, in which the viscous is not in the viscous flow region. Okay, and this is the flow separation. Okay, where the flow separates. Okay, or breaks away, moves away from the wall. Okay, and then it becomes so ed. Okay, turning around, and this is the wake region, and this result in some energy loss. Okay, you can see if it is very smooth, in this case, the wake region is larger. When you have a rod, okay, square rod, in both figures, the flow follows the contours of the body on the upstream sides of the objects. Okay, the region in which a flow follows the body contour is called attached flow. Okay, so this region in which the flow bodies the body contour is called attached flow. This is the region we're indicating. And then when it comes to this point, it breaks away. Okay, it breaks away, which forms the wake region. Okay? When flow separates, the drag force on the body is usually large. Okay, when it separates, the drag force is usually large. Okay, thus designers strive to reduce or eliminate flow separation when designing products such as automobiles and airplanes, because when it separates, the drag force on the body is usually large. We already defined drag force as the force exerted on bodies in fluids. Okay, it can be water, it can be air. Okay, when fluid is moving along that direction of movement, it exerts force on any object it comes across with. Like in this case, this is the direction of flow. So this is an object. So the drag force is exerted on this sphere by the flowing fluid. Okay, and this drag force is maximum in the work region. Okay, it's maximum once it separates. And for the design of automobile and airplane, we want to reduce this drag force. Okay, as such, to reduce it, we may have to, in addition, flow separation can lead to structural failure because the work is unsteady due to vortex shading, and this creates oscillatory forces. As you can see, it's rotating, and these forces can cause structural vibrations, which can lead to failure when the structure's natural frequency is closely matched to the vortex shading frequency. Okay, when the structure's natural frequency is closely matched to the vortex shading frequency, the structure may vibrate. Okay, and that will lead to failure. Flow separation can occur even inside pipes. Okay, in this example, we have flow passing through an orifice in a pipe will separate. Okay, this is an example of an orifice meter. Okay, you have a pipe in which you have an orifice. When the flow is passing through, it separates. Okay, this is the work region. You can see the work region here. Okay, so in this zone, the zone of separated flow is usually called a recirculating zone. Okay, the zone of the separating flow is usually called a recirculating zone. And separating flow within a pipe is usually undesirable because it causes energy losses, low pressure zones, okay, that can lead to cavitation and vibrations. We discussed about how cavitation is caused as a result of having low pressure zones, because once the pressure of the fluid falls below the vapor pressure of the fluid, then you have cavitation to occur. You have bubbles, okay, which reach higher pressure zones and burst and release huge amount of energy, which can lead to scouring effect, which can eat away the pipe materials, okay, and blades in particular, where cavitation usually takes place. Okay, blades, pumps, and all that. So these are undesirable losses. Okay, they cause energy losses. Okay, we don't want such low pressure zones, and these work regions or the recirculating zone, they are prone to low pressure. Okay, and for that, they are also prone to, they can cause a lot of energy losses as well as structural damage. Now, still on the different types of flows, we have internal and external flows. This is very simple. Fluid flow is classified as being internal or external depending on whether the fluid flows in a confined space or over a surface. Okay, if the flow is unbounded, the flow of an unbounded fluid over a surface such as a plate, a wire or a pipe is external flow. Okay, here we mean not inside a pipe but just over the pipe. Okay, it's called external flow. And then if it is inside a pipe in which it is completely bounded, we call it internal flow. Okay, water flow in a pipe, for example, is internal flow. And air flow over a ball or over an exposed pipe during a windy day is called an external flow. And the flow of liquids in a duct, that's like a pipe, is called open channel flow if the duct is only partially filled with the liquid and there is a free surface. The flows of water in rivers, sewers, irrigation ditches are examples of uh, open channel flow. Okay, internal flows are dominated by the influence of viscosity throughout the flow field because of the boundary material, because of the boundary surface, because the fluid material is bounded completely like in a pipe flow. So you have a lot of influence of viscosity. While for external flows, the viscous effects are limited to boundary layers, okay, near the solid surfaces and to work regions downstream of bodies. Like when you have just a plate, The boundary layer is just some few meters, the distance within which you have the viscous effect to be most pronounced. Let's say from here to here. So this forms, let's say, the boundary layer, where the velocity of the fluid particles are affected by the presence of a solid boundary. You can see the velocities above the boundary layer becomes more or less uniform, the same throughout. Okay, meaning they are not affected by the viscosity. Okay, they are not affected by the shear stresses exerted on the wall. Okay, the shear stresses exerted on the wall. And that is why shear stress effects are usually neglected in open channel flows. This I mentioned. For open channel flows, we normally neglect the shear stress effect. Okay, because the shear stress effect is limited to just the boundary layer above the solid surface. While for pipe flow, because you have it from above and below, so it is like parabolic, the velocity profile. So the boundary layer becomes, more pronounced, and the layer of viscid flow becomes very small compared to open channel flow. Okay, so the internal and external flows more or less can have, let's say, pipe flow and open channel flow. Open channel flow is an external flow. Okay, and like I mentioned here under this, that the flow, if the pipe is not full, you can have the flow in which the pipe is not full. This is also treated as open channel flow. Okay, it is also treated as open channel flow because you have a free surface of the water body. Okay, it is treated as open channel flow, and this is usually the flow in sewers. Sewer are the pipes that convey the wastewater from our residential areas to the wastewater treatment plant. In sewers do not flow full, but pipes meant for water supply, okay, they flow full. Okay, and those that do not flow full, like this, or open channel, in which the flow in channels, in canals, in streams and rivers, they are all open channel flows. Okay, I'm still on the internal versus external flows. The fluid flow is classified as being internal or external depending on whether the fluid flow, no, this is the same, it is a repeated slide. Let me note it down. So this I will delete it. This is slide number 38. Now we move to another type of flow, which we call natural or unforced versus forced flow. Here, a fluid flow is said to be natural or forced, depending on how the fluid motion is initiated. Okay? Depending on how the fluid motion is initiated. In forced flow, a fluid is forced, as the word forced, okay? You force something, okay, to flow over a surface or in a pipe by external means, such as a pump or a fan. You use pump, usually, I told you about flow by gravity, okay? If you want water to flow from uh, lower elevation to higher elevation, because higher elevation is having higher energy level because of the potential energy. Okay, so you want flow from lower energy region to higher energy region, then you have to supply energy to the flowing fluid. And how do you supply energy to the flowing fluid? By using pump. Pump basically supply the energy needed to overcome the energy difference between a lower elevation and a higher elevation. Okay, the same thing with fan in case of gas. Okay, so in natural flows, fluid motion is due to natural means such as buoyancy effect. We talked about buoyancy. Okay, when you immerse something in liquid, the buoyant force is pushing it up. Okay, and depending on the density of the body, a lot of things we looked at three scenarios: when the body is floating, and when it is fully immersed, and when it sinks to the bottom. Okay, and one of them is also gravity. Okay, the buoyancy which manifests itself as the rise of warmer and thus lighter fluid and the fall of cooler and thus denser fluid or gravity. Okay, we also discussed about the hot air balloon, okay, in which you heat the air. When you heat it, it becomes lighter, so it flows vertically up. The buoyancy effect will push it up, okay, and you maintain your level when you try to maintain the density of the air, okay, the density of the air by maintaining the same temperature inside the balloon and outside the balloon, because once the temperature is the same, then they will have the same density in that case, okay. And also gravity effect uh, when you have 2 points at different elevations, gravity will move, okay, will force it. That's why whatever you push up, gravity will pull it down, okay, because of gravitational force, okay. So that is why points at higher elevation, they possess higher potential energy, which is the energy they possess as a result of their position in a gravitational field. Okay, so fluid naturally flows from higher energy level to lower energy level. That is the driving force, okay, energy difference. Now, another type of flow which we discussed before is the compressible versus incompressible flow. Here, a flow is classified as being compressible or incompressible depending on the level of variation of density during flow. Okay, we talked about density, isn't it? As in chapter 2. Incompressibility is an approximation in which the flow is said to be incompressible if the density remains nearly constant throughout. The density remains nearly constant throughout. If you look at water, the density of water remains constant throughout flow, okay? So it is incompressible, and most liquids are incompressible because their density do not change even with application of high pressures, but gases are highly compressible. Gases are highly compressible. Okay, so all liquids are usually considered to be incompressible. Okay? Therefore, the volume of every portion of fluid remains unchanged over the course of its motion when the flow is approximated as incompressible. And the densities of liquids are essentially constant, and thus the flow of liquids is typically incompressible. Why do we say it is incompressible? Because the density is essentially constant. The density doesn't change. And what is density? The mass per unit volume. Okay. The mass, of course, doesn't change. The volume is the one that changes. Once the volume changes, remember, density, simply mass over volume. Mass is constant. The volume that is being played around. If the volume decreases, then the density will increase. Okay? And if the volume increases, then the density will decrease. Okay? Because that gives, it means that the same amount of matter is either compressed or it occupies more space. Okay? But if the volume remains the same, mass, will remain the same, definitely, and the density overall will remain the same. And then in that case, just 1 minute. Assalamu alaikum. Yes, how are you? Yes, I'm in a class. Okay. Yeah, okay. All right. Okay, so once the density remains constant, flow is called incompressible. Okay. Therefore, liquids are usually referred to as incompressible substances. A pressure of 210 atmosphere. That is 210 times the atmospheric pressure. You can imagine the amount of pressure, 210 times the atmospheric pressure. Okay, causes the density of liquid water at 1 atmosphere to change by just 1%. By just 1%, meaning the change in volume, okay, as resulting from this, which is the bulk modulus, okay, the bulk modulus of elasticity, okay. So the change in volume is just 1% when you apply this amount of pressure. So that's why they are approximated. Liquids are usually approximated to be incompressible. And gases, on the other hand, like I mentioned, are highly compressible. A pressure of just 0.01 atmosphere. You can see our atmospheric pressure divided by 100, divided into 100, okay? Just this additional pressure, for example, causes a change of 1% in the density of atmospheric air, okay? It causes a change of 1% in the density of atmospheric air. Now, this is a table that summarizes the flow descriptions in terms of the different types of flows: uniform flow, laminar flow, three-dimensional flow, and all that. So it will be very important to understand this table. Okay, it's like a grand summary of the flow descriptions. Okay. Like the work region is the region of separated flow behind a body. The boundary layer is a thin region of fluid next to wall. Okay, and viscous effects are significant in the boundary layer. And here for flow separation again, occurs when fluid particles move away from the wall. Okay? The fluid particles are separated from a solid boundary. Okay? And attached flow occurs when the fluid particles are moving along a wall or boundary. Okay, and they're moving along a wall or boundary. And the region of separated flow inside a pipe or a duct is often called a recirculation zone. We have said a lot about the velocity field, which is what we started with. The velocity field, we use the velocity field to describe the different types of flows, and we use the velocity field to describe the flow in 1, 2, or 3 dimensions, and also use the velocity field to explain also what happens in the work region, flow separation and all that. Okay? And so now we will move to the acceleration field, which is another component, which is the next component, because once velocity changes, then you have acceleration. Okay. Once the direction or magnitude of velocity changes, then you have acceleration. Okay. So let's say some few things about the acceleration field. Predicting forces is important to the designer. Okay. And because forces are related to acceleration, it is important to know what acceleration means in the context of a flowing fluid. And acceleration is a property of a fluid particle that characterizes the change in speed of the particle and the change in the direction of travel at an instant of time, at an instant in time. Okay, so the acceleration is simply dv dt. Okay, you can see anything written in bold here implies it is a vector quantity. Okay, so that's why you have the acceleration A in bold and V in bold, because they are all vector quantities. Okay? So A is given by dV dt. Here we are using total derivative. The equations of motion for fluid flow, such as the Newton's second law, are often written for a fluid particle, which we also call a material particle. If we were to follow a particular fluid particle as it moves around the flow, we will be employing the Lagrangian description, and the equations of motion will be directly applicable. Okay, when we try to follow each movement of the fluid particle, we are using the Lagrangian description. Remember, we explained what is the Lagrangian description of fluid flow as well as the Eulerian description. For example, we would define the particle's location in space in terms of a material position vector. Okay, remember the position vector, in statics. Okay, x, y, z. Okay, this is the material particle, the position vector of the particle at any given point in time. Because all these x, y, z, they depend on time. Okay. However, some mathematical manipulations is then necessary to convert the equations of motion into forms applicable to the Eulerian description. Okay, because the Eulerian description is not talking about particle in per se, but is defining a given region in space, a field in which all particles passing through that region will possess the particular property of that parameter defined by that equation, which is the field. Consider, for example, Newton's second law of motion applied to our fluid particle. The Newton's second law is defined, as when you have an unbalanced force acting on a particle, it accelerates, okay? And this acceleration is proportional to the amount of applied force and is in the direction of the applied force, okay? So at the end, we have F equal ma. F is the resultant force, the net force acting on the particle. M is the mass of the particle, and A is the acceleration of the particle. And we defined acceleration before to be dv dt, okay, which is the acceleration of the particle. Because once you have force acting, the particle will accelerate, okay? So just like a description, you have particle M at this point in time, okay? When you have force acting, it will accelerate in the same direction. The velocity vector can be different from the acceleration vector, I mean, the direction of the velocity vector, okay? When it can change, this is the fluid particle position at t plus dt, okay? And this is its position at time t, okay? So this is at different time. Of course, the position vector will change as well, okay? At t plus dt. At any instant in time, the velocity of the particle is the same as the local value of the velocity field at that location, okay? The value of the velocity of the particle is the same as the local value of the velocity field, okay, at that location, x, y, z of the particle. Since the fluid particle moves with the fluid by definition, okay, the fluid particle, it moves with the fluid by definition. In fact, the fluid particle is part of the fluid particle, okay, it's part of the fluid itself. So the velocity of the particle is a function of x, y, z, and t, okay? It depends on four things. First, the position, which is x, y, and z, and then time. The position x, y, z, they are all functions of time because it is moving, okay? So it changes, the position changes, okay? So the velocity also depends on time. Take the time derivative, acceleration. We must therefore use the chain rule, okay? We must therefore use the chain rule since the dependent variable v is a function of four independent variables, in this case, x, y, z, and t, okay? So how do we apply the chain rule here? Okay, the acceleration of the particle is the total derivative, okay, dv by dt, okay? And dv, v is what? A function of x. This is 1, 2, 3, 4. Okay. So how do we use the chain rule now? We now employ the use of the partial derivative. Okay. Partial derivative, but you know chain rule, you keep one variable constant and differentiate the other one. Okay. You keep one constant and differentiate the other one. So here we use the partial derivative del v by del t. So here we are keeping the position constant, okay? We are keeping the position constant, del v by del t, okay? And then we are differentiating, we are taking t, we are taking the variables one by one, okay? Let me call this 1, 2, 3, 4. So we are starting with the fourth one, okay? Del v by del t, then we're taking the fourth one, dt by dt, okay? You see this, and then plus del v by del x, that is, we're now taking the second one, okay, del v by del x times dx by dt. In all cases, we will use dt because in the total derivative here, we have dt, okay? And then we take the second, the third one, del v by del y, then times dy dt plus del v by del z times dz dt, okay? This is how the chain rule is applied, okay? The first time del v by del t is the partial derivative, and the second one is the total derivative. Definitely dt and dt will cancel out, okay? So del here is the partial derivative operator, and d is the total derivative operator, okay? Now, if you look at it here, del v by del t, is the change in velocity with time when space is constant. Okay, here space is constant. Okay, Then the x dt here, this is now the velocity of the particle in the x direction, isn't it? Which we call u. Okay, dy dt also is the velocity in the v direction, okay, along the y-axis. Dz dt is w, okay, and exactly what we have. You have a particle at this is the initial position, and this is after, it travels after time t plus dt. Okay, so this is the initial position of the particle, x particle, y particle, and then here it will be x plus dx and y plus dy. Okay, so if you consider the second term on the right hand side, dx dt is the velocity u along the x-axis, and v along the y-axis, and w along the z-axis. Furthermore, at any instant in time under consideration, the material position vector of the fluid particle in the Lagrangian frame is equal to the position vector in the Eulerian frame. Okay, the position vector of the particle is equal to the position vector of the Eulerian frame. Okay, so finally, at any instant in time, the acceleration field must equal the acceleration of the fluid particle that happens to occupy this location. Okay, so here we are now transforming this. The acceleration of the particle, which is dv dt, is now del v del t plus u del v del x plus v del v del y plus w del v del z. Okay, so why did we say that at any instant in time the acceleration field the acceleration field of the particle, okay, this one I will need to move it, because the acceleration field of the particle must be equal to the acceleration of the fluid particle that happens to occupy the location, because the fluid particle is moving together with the bulk of the fluid. Okay, so they have the same acceleration. So the field, the Lagrangian description is now converted to the Eulerian description, which is using the field. And because the fluid particle is by definition accelerating, okay, the fluid particle is by definition accelerating with the fluid flow. Hence, we may replace A, which is the acceleration of the fluid particle, with the acceleration field, that is A into xyz t. So we are basically transforming from the Lagrangian to the Eulerian frame of reference, okay, because the acceleration of the particle is defined by the acceleration at any given instant, at any time position in space and time, okay, which is the field. So what are we saying in general? The acceleration of a particle can be expressed in this way, which is this one. It is this one. We are redefining this expression here. Okay. We are using the gradient operator. We are condensing it, okay, using vector calculus now, okay, not vector algebra. So it's equal to dv dt, which is the acceleration field, okay, is the acceleration as a field variable, which is del v del t, which is equal to del v del t, dv dt is equal to del v del t plus v dot del, or gradient operator, times v. What is the del or gradient operator? It simply gives direction to a scalar quantity, okay? It's defined as this, okay? Del by I, del by del x plus j, del by del y plus k, del by del z, okay? So this is compressed form, and when we try to expand it for the acceleration field, ax, okay, become del u del t plus u. So u, v, and w will vary with respect to x, y, z, okay? But here you have del u, del u, del u, okay? Ay will have v throughout, okay, as the numerator, and then we have x, y, z, because v, u, and w, they are all functions of x, y, z, okay? They are all functions of x, y, z, okay? So this is the Cartesian coordinates representation of the velocity field. So the first term on the right hand side, which is this one, del v del t, is called the local acceleration, and is non-zero only for unsteady flows. Okay, because it shows the change in velocity with time. Okay, the change in velocity with time. So if it is a steady flow, for steady flow, we say the velocity do not change. We define del V, for steady flow, if you remember, we said del V del T is equal to 0. So it is only non-zero if if the flow is unsteady. If the flow is steady, then the velocity do not change with time. Hence, this term will be 0. Okay. But the other terms, that's why we call it local acceleration, because here we are fixing the space, the position. We are considering a given point in space. Okay. We are considering space to be constant in this case. Okay, that is a given point in space, and then analyzing is the velocity increasing. So that's why we call it local. Local because it is attached to a given point in space. It is localized. Okay, so we call it local acceleration. Okay, and the second term, which is this one, okay, okay, which in this case, this terms, okay, you see, they all have to do with the variation of the velocity with space in terms of x, y, z. Okay, so we call it advective or convective acceleration, because depending on the fluid, is it liquid or gas, it can be advecting or convecting. Okay, so we basically have local acceleration plus advective acceleration or convective acceleration. All the other terms are the advective or convective acceleration. Okay, and that's because they move in space. Okay, they determine the variation of the velocity with space. Okay, now advective or convective acceleration, this term can be non-zero even for steady flows. Okay, because it's not talking about time. Okay, so even for steady flow, when the velocity do not change with time, the velocity can still change with space, because in that case we are not fixing space. Okay, we are not fixing space, we are fixing time in that case. Okay, meaning at an instant in time is the velocity changing. Okay, over a given space. Okay, so that's why we have the variation of the x, y, z in that case. So it accounts for the effect of fluid particle moving, that is advecting or convecting, to a new location in the flow where the velocity field is different. For example, consider steady flow of water through a garden hose. Okay, consider steady flow of water through a garden hose nozzle. You can see here the flow area is the same. Okay, but once it comes here, the flow area reduces. So when it reduces, we know flow rate mean equal to AV. When the area reduces, the velocity has to increase. So the particles, the flow particles, the fluid particles are accelerated in the area where you have reduction in the cross-sectional area. They are accelerated. Okay, so that's what we define steady in the Eulerian frame of reference to be when properties at any point in the flow field do not change with respect to time. That is when you look at a given space in time, a given point in space, and then analyze, okay, at that point in time, is the velocity changing or constant? That is what we define the steady flow. So since the velocity at the exit of the nozzle is larger than that at the nozzle entrance, the velocity here, let's call it V1, V2. V2 is greater than V1, okay? Then clearly the fluid particles accelerate, even though the flow is steady. Okay, the flow is steady, but the fluid particles accelerate. We call it steady because if you come to this position and analyze the velocity profile at this point, it is not changing. If you come to this position, which is fixing space, okay, and analyze the velocity profile, it is not changing. Okay, but over space, when you vary space now, okay, when you vary the space from this point to that point, the velocity is not the same throughout. So it is steady but non-uniform in this case. Okay, because for uniform, the velocity value has to be the same at every point in space. The acceleration is non-zero because of the advective acceleration terms, okay? The steady acceleration term, which is the local acceleration, will be zero, okay, which is del V del T, it will be zero because it is steady flow. But the advective acceleration terms will not be zero. And this we will demonstrate in the example that we are going to show later. Note that while the flow is steady from the point of view of a fixed observer in the Eulerian reference frame, it is not steady from the Lagrangian system reference frame, moving with a fluid particle that enters the nozzle and accelerates as it passes through the nozzle. From the Eulerian approach, which you fix at a fixed position, the velocity doesn't change. But for the Lagrangian reference frame, in which you track the movement of the fluid particle, okay, you see that the velocity is changing, okay, because the velocity here is v1, which is less than the velocity in v2, okay. Now let's take a few minutes break. Then when we come back, we will take this example where we will demonstrate, where we calculate acceleration field, okay, acceleration of a fluid particle through a nozzle. Yeah, welcome back, gentlemen. Let's take this example. So, it says Nadine is washing her car using a nozzle similar to the one sketched in figure 4.8. This is the nozzle, okay? This is the inlet diameter, which is bigger than the outlet diameter, okay? The inlet velocity, outlet velocity. Uh, so we have the diameters given, okay? The inlet diameter has been provided and the outlet diameter, okay? All provided, and the length, delta x, the length of the nozzle. The volume flow rate through the garden hose, okay, and through the nozzle, that is the discharge, that's the volume flow rate, okay. You see V dot, that is discharge Q, okay, is 0.841 gallon per minute, and the flow is steady, okay. The flow is steady. Estimate the magnitude of the acceleration of a fluid particle moving down the center line of the nozzle, okay, moving down the center line of the nozzle. So that's why it is indicated with the blue, okay, at the center line. That's where, and you know, it will have maximum velocity there because it is the one least affected by shear stress, the boundary shear stress, okay. So now, acceleration following a fluid particle down the center line is to be estimated, and we need to start by laying down our assumption, okay. The flow is steady and incompressible. Already mentioned that it is steady from the problem. Okay, hence del V del T is zero. Our local acceleration will be zero, definitely. And the x direction is taken along the center line of the nozzle. Okay, the x direction is taken along the center line of the nozzle. And by symmetry, you remember, I mean, when analyzing one, two, and three-dimensional flow. So in this case, it will have by symmetry, the velocities along the other axis will be zero. Okay, U and W. So we will have, by considering x direction along the center line, so this is our U. Okay, then the other, because they are perpendicular to V and W, it will have zero component. The velocity will have zero component in those axes. Okay, since our particle is along the U axis, it's not inclined. If it is inclined, then it will have components on V and W axis. That is Y and Z axis. Okay, because just imagine the three. If you look at this to be X, Y, Z. Okay, so the flow is along this axis, okay, which is our velocity, okay, U. This, so what is the component of U on Y and Z? Zero, okay. So that's why we have V and W to be zero along the center line. But U increases through the nozzle. The value of the velocity here, the particle here is accelerated towards the end because of the reduction in the flow area, the cross-sectional area. And that is what we need to find. Now, the flow is steady, so you may be tempted to say that the acceleration is zero. Yeah, the local acceleration is zero. The advective acceleration is not zero. However, even though the local acceleration is identically zero for this steady flow field, the advective acceleration is not zero. We first calculate the average x component of velocity at the inlet and outlet by dividing the volume flow rate by the cross-sectional area. Okay, we know that flow rate Q is equal to AV. Okay, so we want to find the velocity, okay, at the inlet and outlet. Okay, so here the velocity is going to be Q over A. Okay, in this notation, Q is written as V dot. Okay, okay, so just not this. Okay, so we do this for the inlet and the outlet. Okay, because Q is constant, but the area changes because of the diameter. Okay, because the area is circular pi d squared. The inlet, okay, is different, is different from outlet. So this is the velocity for the inlet, 1.95 feet per second. And when we do the same thing for the outlet, the velocity for the outlet is 10.4, almost five times higher than the inlet velocity. So in this case, we need to find the average velocity. Okay, we now calculate the acceleration in two ways with equivalent results. So we'll use two methods, method A and method B, and all the methods give us the same result, similar result. Okay, so for a simple average value of acceleration, the x direction is calculated based on the change in speed divided by an estimate of the residence time. That is the time it took to move from this point, from the inlet to the outlet. Okay, that is the residence time. Okay, and the residence time is given by the change in space delta x over the average velocity. Because velocity is simply dx dt. Okay, so delta t will be delta x over the average velocity, because the velocity changes from the inlet. Okay, the outlet is different from that of the inlet. And by fundamental definition, acceleration as the rate of change of velocity, so acceleration in the x direction is delta u over delta t. Okay, and then delta u is the difference in velocity from the outlet minus inlet, and delta t is what? Is equal to delta x over the average velocity. Okay, over the average velocity, because we are considering this region. Okay, so what is the velocity here? The velocity is, we have velocity different from the velocity at this point. Okay, so that's why we have to find the average velocity. Average means you sum inlet plus outlet over 2. So that's why we have u outlet plus u inlet. Then these two will come up. Okay, so, and this will go and multiply this to have this formula. This is simple. Let me just do it here. Not waiting. Okay, u outlet minus u inlet over delta x divided by the average velocity. And so the average velocity will just go and multiply this out. Okay, so you will have u out minus u in over delta x times the average velocity, which is u out plus u in over 2. So that's why 2 will multiply delta x. And then this is difference, of two squares. Okay, so when you multiply this and this, you will arrive at u squared o minus u squared I. And then we have the values. We just substitute. Delta x is provided in question. We already found ui and uo. Okay. Now the second method, which is method B, this is the acceleration vector. Okay, the acceleration in the x component. This is steady, so it's 0. Okay, in the u and w direction, v and w are 0, so these terms will go. So we have only this term, okay, which is now the average velocity along this distance. Okay, now delta u is simply uo minus ui, and this is the average velocity here. Okay, when we multiply it out, we have the same thing we had in the first method. Okay, the first method, we just use the simple definition of acceleration, delta u over delta t. Okay, and substituting the values, we have the acceleration to be 160 feet per second squared. Okay, here fluid particles are accelerated through the nozzle at nearly 5 times the acceleration of gravity. Okay, 5 times the acceleration of gravity. Okay, this simple example clearly illustrates that the acceleration of a fluid particle can be non-zero, okay, even in steady flow. And note that the acceleration is actually a point function, whereas we have estimated a simple average acceleration through the entire nozzle. Okay, through the entire nozzle. So the average acceleration through the entire nozzle from the inlet to the outlet. How is the particle becoming accelerated? Okay. In the next class, we will take the Euler's equation. But one of the students told me that he has a midterm lab at 11. So for that, I will administer the quiz now, okay, so that he can have time to quickly come for the midterm lab. Okay, so I will post the question for the midterm lab, solve it, and send it to my WhatsApp. Okay, just 15 minutes. Any question? I have already updated, but I will update it again from the next section. That's the Euler's equation. Like I said, I will try to make up lecture on Saturday. Okay, I will try my best to see that I do it. Okay.